All right, greetings everyone. The purpose of this video is to go over a couple of examples of solving rational inequalities. Now, unlike some of my other videos, the material from this will be coming from a different textbook. This will not be coming from the Littman-Rasmussen pre-calculus textbook, since this topic is not covered in there. Instead, this will be coming from a textbook by OpenStax. And section 4.6 out, or excuse me, 7.6 out of that textbook. Okay, so from materials earlier in the course, we've learned to solve an inequality like this one, where we're given x minus 1 times x plus 2 squared less than or equal to 0. And in those examples or those types of problems, what our approach was to first look at what would make this left-hand side equal to the right-hand side, namely the values of x that make that equal to 0. In this case, by inspection, we can look at each of those and see that x equals 1 makes this 0, x equals -2 makes this 0. And then once we had those values, we would go ahead and draw a number line. We would mark them on there in order from left to right. So since -2 is smaller, it would come to the left. 1 would go to the right. And then I'd put a reminder here to remind myself that at each of those points, they make this expression over here on the left, this x minus 1 times x plus 2 squared equal to 0. And then from there, what we do is we choose test points. So maybe -3 here, since that's a value less than -2, a point in between -2 and 1, which would be 0, and then a point bigger than 1, which would be 2. We'll take each of those and plug them in one by one in for x and see what we get. And in each case, what we're looking for is whether or not we get a positive or negative value. And what that tells us, for example, if we plug 2 in there, we would get a positive value, is that for all of the numbers in this interval that 2 falls in, so all the numbers bigger than +1, the expression will result in a positive value. And you could check that by checking other values. You could plug in 3, you could plug in 1.5, you could plug in 1 million if you wanted to. But what you would find out is that for any value there bigger than 1, you would get a positive value. Then we do the same thing for 0 and the same thing for -3. And then we use what we find for each of those intervals to then answer the question or to solve the inequality, namely find the intervals where the function is less than or equal to 0. Okay, so let's look at how this would apply to a rational inequality. Now, first of all, what we see here is this is a rational inequality, since we notice that the expression on one side is rational, since it has a numerator and a denominator and a polynomial in each of those. And also an inequality, since we see the greater than or equal to 0. Now, in order to solve this, much in the same way that we did on the previous one, we want to figure out what makes this expression equal to 0. And as we have discovered, the way to do that is to figure out what makes the numerator equal 0. In particular, to solve t squared minus 3t minus 10 equals 0. Now, from techniques we have learned earlier in the course, we know a few different ways to solve this. We could try the quadratic formula. In this case, this one factors very nicely to t minus 5 times t plus 2. Since we hopefully note that -5 times +2 is -10, and -5 plus 2 would be -3. And then from there, we can solve and find that we have two values of t that make this equal to 0, t equals 5, and t equals -2. So we know that those would be now two of our important points for this expression, since they make the numerator equal to 0, and we would use those as we get ready to draw a number line. However, with rational functions, there's an additional piece we need to think about, and that's the denominator. Okay, so as we've seen with rational functions, important points related to the denominator are points that make the denominator equal 0. Those are what cause vertical asymptotes in the function. And it turns out that for our rational inequalities, they're also important. So in this case, we know since the denominator there is t minus 3, that the value that makes that equal to 0 is t equals 3. And that's important because if we were to take and plug in 3 now into this expression for t, if we did that, we'd have 3 squared minus 3 times 3 minus 10, all divided by 3 minus 3. If we work out the numerator there, I think we end up with 9 minus 9 is negative 10. But in the denominator, the 3 minus 3 gives us 0. We're doing negative 10 divided by 0, which we know is no bueno, right? That equals undefined. So we don't actually get an output value there, okay? And again, we know that the function is undefined there. So that's going to be important as we go now to set up our number line and try to figure out the values that solve this inequality. So what I'm going to do is set up my number line here. I'm going to mark all 3 of those values that we found in numerical order. So the lowest we have is negative 2. The middle value will be 3, and then our higher value will be positive 5. And again, for a reminder for myself, I'm going to mark what we get if we plug each of those values into the expression. Well, negative 2 and 5, we know both of those give us 0. Since those values make the numerator equal 0, if the numerator equals 0, the whole expression equals 0. And then also at t equals 3, I need to mark that the function is undefined there. And again, if you were to graph this expression, what you would see is a vertical asymptote. Okay, so the function does not have an output value there. And then from there, we proceed in the same way that we would with polynomial inequalities, is we will choose numbers that fall into each of the intervals we've created, or that our number line has been divided into by these 3 values, plug them into the expression, and find out whether they make it positive or negative. So I'll start with a value less than negative 2. For simplicity's sake, I'm going to do negative 3. So I will use t equals negative 3 here. Go ahead and plug that in for t into the function. So I had negative 3 squared minus 3 times negative 3 minus 10, all divided by minus 3 minus 3. If we work that out, I believe what we end up with in the numerator, we'll have 9 plus 9 is 18 minus 10 is 8. The denominator, negative 3 minus 3 is negative 6, which now reduces to negative 4/3. And as we saw before, the most important thing here is that this is negative. And so what we know is that for all values less than negative 2 in this interval over here, the expression outputs negative values. Okay. And again, you could check additional values if you want to, but you should find that they all end up being negative. All right, we'll proceed on. We'll now find a value between negative 2 and 3. I'm going to use 0. If I plug in t equals 0 here, by plugging 0 in for t, would be positive 10/3. And so most importantly, we see that it is positive. So we know for all values between negative 2 and 3, the expression will output positive values. Continue on from there. Between 3 and 5, I'm going to use 4. So plug in t equals 4 into the expression. When we do that, we find that it will come out to be negative 6. And again, you can check this yourself by plugging t in up there. And most importantly, again, it is negative. So we know that for all values between 3 and 5, this expression outputs negative values. And then finally, we choose a value bigger than 5. I'm going to use 6. So t equals 6. We plug this in here. And what we'll find is that we get 8/3 in this case. And again, most importantly, that's a positive 8/3. So we know that for all values bigger than 5, this function outputs positive numbers. And now with that, we are ready to go ahead and solve the inequality or write our solution. Because notice what we're looking for here is values of t that will make this expression greater than or equal to 0. So we're looking for the values that the outputs, the set of outputs that make this greater than or equal to 0. Well, if I take a look at my number line, first of all, I'm looking for values greater than 0. I know that those are going to be the values where the function is positive. So that looks like that'd be between -2 and 3, and also for the values bigger than 5. But we also have this equal to requirement, right? It says greater than or equal to. So we also want to include the values where it is equal to 0, which again, from our number line here, we would see happens at -2 and +5. So if we take this solution and convert it now into interval notation, we see that the intervals where this function or this expression is bigger than or equal to 0, they start at -2, and we include -2 since it's equal to 0 there. Goes up to, looking at that first interval, up to 3. But then we are not going to include 3 because at that point the function is undefined, or the expression is undefined. So it is not greater than or equal to 0. It's just undefined. And then we have a break in our response, right? Because between 3 and 5, there is not any values that are greater than or equal to 0. At 5, we find that the function is equal to 0. And since that's greater than or equal to 0, we'll include 5. And then we're looking at all values bigger than 5, which means we go up to positive infinity. So our solution in this case would be bracket -2, comma 3, union, bracket 5, comma infinity. So that's for that example. All right. Now let's look at an example that is a little bit different. Now in this case, notice we have a rational inequality. We notice that we have a fraction on the left-hand side. But this time on the right, rather than having 0, we have a non-zero number. In this case, we have -3, which at first might give you pause because the examples we've looked at have only been greater than or equal to 0 or less than or equal to 0, something like that. It might make this one look more complicated, but we can start here by making this so that we have 0 over here on this right-hand side. And in order to do that, we just go ahead and add 3 to both sides. As soon as we do that, the -3 plus 3 gives us 0 on the right. We have greater than, and then we have x minus 3 over x plus 6 plus 3. We can't combine this plus 3 with any of these since it doesn't have any x's. And now we have an expression greater than 0, and we can proceed in solving it the same way we did as the previous one. Now, another potential issue we run into here is we now have kind of two separate expressions on the left, whereas on this one, right, everything was together in one expression on the left. But we can still deal with this because what we can do is combine or kind of add together those expressions on the left to make them into one single expression. Here's how we do that. Since the x minus 3 over x plus 6 is a fraction, I'm going to make this 3 over 1. So it's like we're adding two fractions. And we know that when we add two fractions, we need to have common denominators. So I need to find a common denominator between x plus 6 and positive 1. In this case, since the second denominator is 1, we can just choose the first one, x plus 6, as our common denominator. So I want to change both fractions so that they have the same denominator, have that x plus 6 denominator. And in the case of the first expression, right, we did not change the denominator. It was originally x plus 6. It's still x plus 6. So this will stay as x minus 3 in the numerator. For the second expression, the denominator was originally 1. We've changed it to x plus 6. And the way we do that is by multiplying 1 times x plus 6. Since we did that in the denominator, we also need to do it in the numerator. So I'll take the 3, multiply that by x plus 6. We can go from there. Now we do some simplifying in the second expression. So we'll have x minus 3 over x plus 6 plus, we can distribute there in the numerator. So I have 3x plus 6 over 3x plus 18. Excuse me. Put the wrong number there. And then we have x plus 6 in the denominator. Now that we have common denominators, we can now add these two. The way that we add things with common denominators is we add their numerators. So this will be one big expression with x plus 6 in the denominator. So we have the first numerator, x minus 3, plus the second one, which is 3x plus 18. And then if we combine like terms there, we will have x and 3x, which will give us 4x. And then we have minus 3, positive 18. If we add those two together, we end up with positive 15 all over x plus 6. So now what we've done, if we kind of trace back our steps here up to where we started this process, is we've converted the original given rational inequality, the x minus 3 over x plus 6 greater than negative 3, into, or we've simplified it some, to 4x plus 15 all over x plus 6 is now greater than 0. And if we can solve this rational inequality, we can now solve the original one. Okay, the solutions will be the same. So we'll go ahead and work on that. And we'll approach it the same way we did the previous one. So we want to find out what makes the numerator equal to 0, because that will make the whole expression equal 0. Figure out what makes the denominator equal to 0, because that's where the function is undefined. Then we'll draw our number line and use our test points. So starting this one, in the numerator, the 4x plus 15. So we can find what makes that equal 0, although it's a little more difficult to do by inspection. We could set up an equation here, subtract 15 from both sides and divide by 4. So we'd find that this is 0 at negative 15 over 4. So that makes the whole expression equal 0. And then for the denominator, x plus 6, we know x equals negative 6. We'll make that equal to 0. And in fact, that makes the whole expression undefined. So with those two now, go ahead and set up our number line. I'm going to mark these two values on here. Put the smaller one to the left, which in this case will be negative 6. Larger one to the right, negative 15 fourths, which is about the same as negative 3 and 3/4. And we know again at negative 6, this expression is undefined, since that makes the denominator equal 0. And at negative 15/4, it's equal to 0, since that makes the numerator equal 0. And then from there, we choose our test points. So one value less than negative 6, which would be negative 7. A value between negative 6 and negative 15 over 4. For simplicity's sake, I'll use negative 5. And then a value bigger than negative 15 over 4s, which would be 0. We'll take each of those, plug them into the original expression. And remember, what we are looking for here is the answers we get, whether they are positive or negative. So leave it to you all to check this work I have. But if I plug in negative 7, I believe that the answer comes out to be positive 13. If we plug in negative 5, I believe we actually get an answer of negative 5, and then plug it in 0, we'll get positive 5/2. which if we then use that to label the areas in our number line, since -7 gave us a positive number, we know that for all values less than 0, or less than -6, excuse me, the expression gives positive values, excuse me. Between -6 and -15/4, since -5 gave us a negative value, we know everything in there will be negative. And then since 0 was bigger than -15/4 and it gave us a positive number, we know that for all values up there, we have positive. Okay, and now with that information, we can write our solution. And we note that we had converted this the given problem into solving where this one over here on the right is bigger than 0. So we're looking for all values or all intervals where on our number line we're greater than 0. We see that it occurs for the values less than -6. So we'd have -infinity up to -6. The function or the expression is undefined at -6. So we will not include that. And then we'll union that with the other place we see where the values are greater than 0 would be bigger than -15/4, since they're positive. However, in this case, we would not include -15/4 since the function is, or the expression is equal to 0 there, and we're looking where it's greater than 0. So we'd have -15/4 up to positive infinity. And again, since that solution solves this, it will also solve the original expression or inequality that we started with. Okay, that's it for now. Thank you for watching.